What if everything we see, the stars, the planets, the very fabric of space itself, is just a fraction of what's truly out there? Picture standing in front of a door, knowing there's something extraordinary behind it, but you can't open it. That's the unsettling beauty of our universe. It might be hiding entire dimensions right under our noses, layers of existence so strange and vast they defy everything we think we know. For centuries, we've gazed at the night sky, convinced we're seeing the full picture. But what if we're only glimpsing shadows on the wall of a far grander reality? This isn't science fiction. Some of the brightest minds in physics and cosmology are chasing theories that sound like they're ripped from the pages of a fantasy novel. Extra dimensions curled up tighter than a coiled spring, parallel universes brushing against ours like unseen ghosts, even the possibility that gravity itself might be leaking into our world from somewhere else entirely. These ideas aren't just wild speculation. They're serious attempts to solve the universe's biggest mysteries, from the bizarre behavior of black holes to the unsettling fact that 95% of the cosmos is made of stuff we can't even detect. That's where today's journey begins. We're diving deep into 30 of the most mind-bending theories about the hidden dimensions of existence, ideas that stretch the limits of imagination while clinging to the rigor of science. Some will make your brain ache. Others might sound too strange to be real, but each one is a piece of a puzzle that could rewrite our understanding of reality itself. So buckle up. By the time we're done, you might never look at the universe or even the space around you the same way again. Imagine the universe as a symphony, each particle, each force, a note played on invisible strings. That's the heart of string theory, one of the most ambitious ideas in modern physics. It suggests that if we could peer into the fabric of reality with a microscope powerful enough, we wouldn't see tiny dots of matter, but vibrating loops of energy, strings. And here's where it gets wild. For the math to work, these strings can't just dance in the 4 dimensions we know. They need at least 6 more, curled up so tightly they're hidden from view. Think of those extra dimensions like the grooves on a vinyl record. From across the room, it looks flat at just 2 dimensions, but up close, you realize there's a whole spiral world etched into its surface, too fine to see. That's how string theory imagines these hidden dimensions compressed into spaces tinier than an atom, influencing everything from how particles collide to why gravity feels so weak compared to other forces. Some physicists even suggest gravity might be leaking into these coiled dimensions, explaining why it's so much fainter than electromagnetism or nuclear forces. But how do we know these dimensions aren't just mathematical fiction? Experiments like the Large Hadron Collider hunt for clues, tiny energy signatures, or unusual particle behavior that might betray their existence. So far, no smoking gun. Yet the math keeps drawing scientists back like a puzzle missing pieces we can't quite visualize. If string theory is right, reality isn't just stranger than we imagine, it's stranger than we can imagine, with dimensions folded into the fabric of space like origami we're only beginning to unfold. Now picture our universe not as a solitary stage, but as a sheet of paper floating in a vast ocean of higher dimensions, an ocean physicists call the bulk. This is where string theory takes an even stranger turn with the idea of branes, short for membranes. These aren't just abstract concepts, they're colossal structures that could house entire universes like ours, drifting through dimensions we can't perceive. Our universe might be a 3-dimensional brain trapped like a shadow on a wall, while gravity, the odd one out among forces, could be the only one powerful enough to reach beyond it. Why would gravity be so different? Imagine throwing a pebble into a pond. The ripples spread across the water's surface, but some energy also leaks downward into the depths. If our universe is a brain, gravity might behave like those ripples, seeping into the bulk while other forces, like electromagnetism, stay confined to our membrane. That could explain why gravity feels absurdly weak compared to, say, a tiny magnet lifting a paperclip against Earth's entire gravitational pull. The rest of gravity's strength might be dissipating into dimensions we can't see. This isn't just a clever metaphor, it's a hypothesis with real teeth. Some models suggest that if another brane drifted close to ours in the bulk, the collision could have sparked something as cataclysmic as the Big Bang itself. Others propose that tiny black holes formed in higher dimensional space might evaporate instantly, leaving behind faint traces like cosmic breadcrumbs. The Large Hadron Collider has even hunted for these disappearing black holes, though none have shown up yet. The sheer scale of these ideas is dizzying. If branes exist, there could be entire parallel universes hovering millimeters away in a dimension we're blind to, separated by a gap as small but impassable as the width of a single atom. It's like living in a house of mirrors where every reflection might be a real, thriving cosmos forever just out of reach. And if gravity truly leaks into the bulk, one day we might find its fingerprints anomalies in particle collisions, distortions in spacetime, or ripples in the cosmic microwave background. Until then, the bulk remains the ultimate cosmic hide and seek, with the universe whispering clues we're only beginning to decode. But what if our entire universe, every galaxy, every atom, even your own thoughts, is nothing more than an incredibly detailed illusion? This is the audacious claim of the holographic principle, a theory so radical it suggests reality as we know it might be a cosmic mirage. Imagine a movie screen projecting a three-dimensional world, except the screen itself is flat. Just two dimensions holding all the information needed to create the illusion of depth. The holographic principle argues our universe works the same way, with all the data that makes up our three-dimensional reality actually encoded on a distant, two-dimensional surface we can't perceive. This idea didn't come from nowhere. It emerged from a paradox about black holes, those cosmic vacuum cleaners that devour everything, even light. When matter falls into a black hole, it seemingly vanishes forever, violating a fundamental law of physics: information can't be destroyed. Physicist Leonard Susskind and others proposed a solution. What if the information isn't lost, but smeared like invisible ink across the black hole's event horizon, the point of no return? That boundary, a two-dimensional surface, might somehow preserve every detail of what fell in. Take a moment to let that sink in. Every person, every planet, every particle in our universe could, in theory, be translated into bits of information like pixels on a screen, etched onto some unimaginably distant boundary. It's as if reality is a painting and we're just brushstrokes on a canvas we'll never see. This isn't just philosophy, the math checks out. The equations governing black holes and quantum mechanics align eerily well with the holographic principle, suggesting there's a hidden layer to existence where information is more fundamental than space or time. Could we ever prove such a mind-bending idea? Some physicists look for subtle glitches in the fabric of space-time, tiny pixelations or blurring at the smallest scales, like detecting the graininess of a digital image if you zoom in enough. Others study the cosmic microwave background, the afterglow of the Big Bang, searching for anomalies that might hint at an underlying code. While we're far from definitive proof, the holographic principle forces us to ask a haunting question. What if the universe isn't just stranger than we imagine, but stranger than we can imagine, a shadow play cast by a reality we're only beginning to decode? If the holographic principle is correct, it means the very fabric of spacetime, the stage on which planets orbit and light travels, might be nothing more than an elaborate projection. But how do we test something so abstract? Enter the holometer, a groundbreaking experiment at Fermi Lab designed to hunt for the pixelated graininess that could betray reality's true holographic nature. This isn't science fiction, it's a laser-powered microscope probing the universe at scales 1 billion times smaller than an atom, searching for faint vibrations in spacetime itself. The idea is simple yet profound. If space-time is fundamentally pixelated like a digital image, there should be a limit to how smooth it can appear at the tiniest scales, a kind of quantum static fizzing beneath everything. The holometer fires twin laser beams down two 40-meter tunnels, precisely measuring whether their paths wobble unpredictably due to this proposed spacetime noise. If detected, it would be like discovering the universe has a resolution limit, just as a photograph blurs when you zoom in too far. Not everyone is convinced, of course. Critics argue the holometer's sensitivity might still not be enough to catch these fluctuations, assuming they exist at all. Some theorists propose alternative explanations for quantum gravity, like loop quantum gravity, where spacetime isn't holographic but woven from tiny, indivisible loops. Others suggest that even if the holographic principle holds, the effects might be too subtle for current technology to spot, like trying to hear a whisper in a hurricane. Yet the stakes couldn't be higher. If evidence emerges, it would mean reality operates like a cosmic hard drive, with information packed onto a distant two-dimensional surface we'll never see. Black holes, quantum entanglement, even the passage of time, all might be reinterpreted through this lens. Imagine explaining the universe not as a place but as a process, a dynamic exchange of data on an unfathomably vast screen. The holometer may not have found proof yet, but its very existence forces us to confront a tantalizing possibility. The universe might not just contain secrets, it might be one. While Einstein was reshaping our understanding of space and time in the early 20th century, another physicist, Theodore Kaluza, was quietly working on something even more radical, a universe with 5 dimensions. His idea was shockingly simple. What if electromagnetism wasn't a separate force from gravity, but just gravity leaking into an extra dimension we couldn't see? Kaluza sent his equations to Einstein in 1919, and the reaction was telling. At first, Einstein dismissed it as mathematical trickery until he realized the numbers actually worked. The equations for gravity in 5 dimensions didn't just describe gravity, they perfectly reproduced Maxwell's laws of electromagnetism too. It was as if the universe had been whispering a secret in a language only geometry could translate. But if there's a 5th dimension, why can't we see it? That's where Klein stepped in a few years later. He proposed that this extra dimension wasn't stretched out like the ones we know, it was curled up into an impossibly tiny loop smaller than an atom. Imagine a garden hose. From a distance, it looks like a simple line, but up close you realize it's a cylinder. If ants lived on that hose, they might never notice the circular dimension unless they were small enough to crawl around it. That's how Klein imagined our reality, with hidden dimensions coiled so tightly, even our most powerful microscopes miss them. Today, Kaluza-Klein theory isn't just a historical footnote, it's the foundation for modern attempts to unify physics. String theory and brain-world scenarios borrow its core idea. That extra dimensions could be the missing link between gravity and quantum mechanics, but proving it. That's the challenge. Some researchers hunt for Kaluza-Klein particles, hypothetical echoes of particles vibrating in these hidden dimensions, while others look for anomalies in gravity at microscopic scales. The beauty of Kaluza and Klein's work is its audacity. They dared to suggest that the universe isn't just bigger than we thought. It's structured in ways we're literally unequipped to perceive. And if they were right, it means every force, every particle might just be the shadow of something far grander, vibrating in dimensions folded like origami beneath the surface of reality. One of the most startling solutions to gravity's puzzling weakness comes from physicists Lisa Randall and Randall-Sundrum. Their theory paints a picture of our universe suspended between cosmic membranes in a warped 5th dimension, a realm where gravity doesn't just leak, it plunges. Imagine 2 sheets of paper floating parallel in water, one representing our universe and the other a shadow brain we can't see. But here's the twist, the space between them isn't flat. It's curved like a steep valley, with gravity's strength diluting exponentially as it struggles uphill from the shadow brane to ours. This warping explains why gravity feels feeble compared to other forces. Electromagnetism and nuclear forces are trapped on our brain, like actors confined to a stage, while gravity is the lone performer free to wander into the wings, except those wings are a hyperdimensional abyss. The math reveals something extraordinary. 99% of gravity's true strength could be anchored near the shadow brane, with only a ghostly 1% reaching us. That's like trying to hear a concert from outside the stadium. You catch faint echoes while the real vibration shakes the walls elsewhere, but Randall-Sundrum didn't stop there. They proposed a stripped-down alternative, a single brane adrift in infinite higher dimensional space, where gravity's weakness stems from its ability to spread thinly like butter scraped over endless toast. This version trades the elegance of two branes for simplicity, suggesting our universe might be a lone island in a sea of extra dimensions. Both models have tantalizing implications. If gravity does bleed into a warped dimension, colliders might one day detect heavy, Kaluza-Klein gravitons, particles that briefly tunnel into the fifth dimension before snapping back to our brain like cosmic rubber bands. Meanwhile, astronomers scrutinize neutron stars for anomalies in gravity's pull, hunting for deviations that could hint at hidden dimensions bending its influence. The sheer audacity of these ideas lies in their inversion of intuition. We're used to thinking of dimensions as passive backdrops, but in Randall-Sundrum's universe, they're active sculptors, warping reality's rules in ways we're only beginning to map. Whether right or wrong, their models remind us that the cosmos might not just have secrets, it might be built from them. If string theory is a symphony, then M-theory is the conductor, revealing a hidden harmony between what once seemed like competing ideas. It's here, in the tangled web of 11 dimensions, that physicists see the first glimmers of a theory of everything. Back in the 1990s, researchers realized that the 5 distinct versions of string theory weren't rivals at all. They were different faces of a single, deeper framework, like seeing shadows of the same object cast from different angles. M-theory, as it came to be known, didn't just unify these theories. It demanded an 11th dimension to make the math sing. Picture those extra dimensions not as simple loops or folds, but as intricate shapes called Calabi-Yau manifolds, multidimensional landscapes so complex they resemble crumpled paper blown up to cosmic scales. These aren't just abstract doodles, they dictate how particles vibrate, what forces emerge, even why our universe has the exact structure it does. A single change in their geometry could rewrite reality entirely, swapping electrons for massless photons or erasing gravity altogether. It's like tuning a piano with a billion keys. One twist and the music of the universe becomes unrecognizable. But why 11 dimensions? Here's where supersymmetry enters, an elegant symmetry that pairs every known particle with a heavier, unseen twin. In M-theory's framework, these sparticles aren't just convenient math, they're vibrations threading through hidden dimensions, stabilizing the entire edifice. Without supersymmetry, the equations collapse like a house of cards in a breeze. Yet decades of particle collider experiments, including the Large Hadron Collider's relentless searches, have found no trace of these predicted twins. Some theorists whisper that sparticles might hide in dimensions curled tighter than we've probed, while others wonder if M-theory's beauty is a siren song leading science astray. Testing M-theory directly feels like trying to taste a color. Our tools aren't just inadequate, they're conceptually mismatched. If extra dimensions exist at energies a quadrillion times beyond what our colliders can reach, evidence might forever hover out of grasp. Still, some hunt for indirect clues, anomalies in quantum entanglement, patterns in the cosmic microwave background, or even gravitational waves from colliding branes echoing across the bulk. The irony is exquisite. A theory proposing hidden dimensions might itself remain just beyond the edge of detection, a ghost in the scientific machine. What makes M-theory irresistible isn't just its ambition, it's the way it reframes failure. Every dead end, every undetected sparticle forces physicists to ask, are we missing something fundamental, or is the universe more inventive than our grandest theories? For now, M-theory stands as a cathedral of mathematics, its spires stretching into dimensions we can't see, a reminder that sometimes the most profound truths are the ones we can't yet touch. What if our universe is just one bubble in an endless cosmic froth, drifting through dimensions we can't perceive? This is the heart of eternal inflation, a theory that reshapes the Big Bang not as a singular event, but as an unending process, a fireworks show where new universes keep bursting into existence, each with its own rules. Picture a pot of water boiling violently, with bubbles constantly forming, expanding, and sometimes colliding. Now imagine each bubble isn't steam, but an entire cosmos, its physics locked in the moment it was born. Some might have gravity 1,000 times stronger. Others could have light that moves slower than a crawling insect. In this sea of universes, ours is just one accidental arrangement where atoms stuck together in a way that made life possible. A cosmic lottery win we didn't even know we'd entered. The math behind this idea comes from quantum fluctuations, those tiny, unpredictable jitters in the fabric of space-time. During the universe's initial exponential expansion, inflation, these fluctuations didn't just smooth out. Some regions kept stretching, creating pockets where inflation never stopped. Each of these pockets pinched off into its own isolated universe, sealed away like a soap bubble floating free. The chilling implication: there's no reason these bubbles would share the same physical constants. The speed of light, the strength of gravity, even the number of dimensions could be rearranged at random. In some, stars might never form. In others, matter could dissolve instantly. Our universe's delicate balance where particles attract just enough to build galaxies, but not so much that everything collapses, might be a fluke among infinite failures. But how would we ever detect these other bubbles? One clue might lie in the cosmic microwave background, the afterglow of the Big Bang. If a neighboring universe once bumped against ours, the collision could have left a bruise, a strange pattern of hot or cold spots in the sky, like a fingerprint smudged on glass. Astronomers have searched for these anomalies, and in 2010, a team claimed to have found 4 unusual circular patterns in the data. The excitement was short-lived. Later analysis suggested they might just be statistical noise. Still, the possibility lingers. If bubble universes exist, their ghostly imprints could be hiding in plain sight, woven into the oldest light we can see. The most haunting part: if eternal inflation is real, then the multiverse isn't just a place, it's a process, endlessly churning out new realities where every imaginable law of physics plays out somewhere. There could be universes where time runs backward, where black holes spontaneously birth new dimensions, or where space itself is knotted into infinite labyrinths. And somewhere in that froth, our universe is just one accidental arrangement, a single note in a symphony without end. Why does our universe have exactly 3 spatial dimensions, not 2, not 5, but the perfect number for life to exist? This is the heart of the anthropic argument, the idea that we observe this specific dimension because it's the only one where observers like us could emerge. Imagine a universe with only 2 dimensions. Planets couldn't orbit stars without collisions. Gravity would pull everything into chaotic spirals. Now picture 4 spatial dimensions. Gravity would weaken so rapidly that stars couldn't hold themselves together. 3 dimensions, it turns out, is the cosmic sweet spot, stable enough for atoms to bond, but flexible enough for complexity to arise. This isn't just numerology. The physics of higher dimensions gets messy fast. In 4 dimensions, for example, Newton's inverse square law for gravity becomes an inverse cube law, rendering planetary orbits unstable. Electromagnetic forces would scatter unpredictably, preventing the delicate dance of electrons that build molecules. Even the structure of DNA relies on three-dimensional geometry. Its iconic double helix couldn't form in flatland. The anthropic principle suggests we're not seeing some grand design, but a simple cosmic filter. Only in universes with the right dimensionality could life evolve to wonder about it in the first place. But not everyone buys this explanation. Physicist Paul Steinhardt, a vocal critic, argues the anthropic principle is a cop-out, a way to avoid digging deeper into why our universe's parameters are so finely tuned. He champions alternatives like the cyclic model, where dimensions might shift over unimaginable timescales, or the idea that our perception of three dimensions is an illusion baked into the physics of a higher dimensional reality. Others propose that the laws we observe aren't fixed at all, but emerge dynamically like wrinkles forming in cooling metal. The debate exposes a deeper tension in cosmology. Do we accept our universe as a rare accident or insist there's a mechanism, still hidden, that forces dimensions to settle into life-friendly configurations? For now, the answer might lie in the math. String theory's landscape of possible universes suggests countless variations could exist, most barren, with ours a statistical fluke. But until we find evidence of those other worlds, the anthropic argument remains both a profound insight and a tantalizing puzzle, a reminder that sometimes the universe's most basic features might also be its strangest. What if everything around us, the stars, the trees, even the thoughts in your head aren't real, but lines of code written in a universe with more dimensions than we can fathom? This is the startling premise of simulation theory, an idea that suggests our entire reality might be an artificial construct, a digital sandbox built by advanced beings in a higher dimensional world. Think of it like a video game, except instead of pixels on a screen, every atom, every law of physics is generated by rules we can't perceive. Philosopher Nick Bostrom framed this as a trilemma. At least one of these statements must be true. Either nearly all civilizations go extinct before reaching technological maturity. No advanced civilization ever runs ancestor simulations, or we're almost certainly living in one. Bostrom's argument hinges on probability. If a civilization could one day simulate conscious minds, why wouldn't they? And if they did, the number of simulated beings would dwarf the original biological ones, making it statistically more likely we're among the simulations. But here's where it gets stranger. If our creators are themselves simulations nested inside another layer of reality, like cosmic matryoshka dolls, there's no telling how deep the rabbit hole goes. Each layer could operate with entirely different physics. Perhaps time flows differently in their universe, or causality works backward. The ethical implications are staggering. If we're simulations, do our actions matter? Some argue it changes nothing. Pain and joy feel real to us, so they are real. Others warn of a moral crisis. If our creators could intervene in suffering but choose not to, they become akin to indifferent gods. And what if we one day create our own simulations? Would pulling the plug on them be genocide, or just closing a program? Evidence for this theory is unsurprisingly elusive. Some point to glitches in quantum mechanics, particles behaving unpredictably as potential artifacts of computational shortcuts. Others suggest that if the universe is a simulation, it might have a resolution limit, a smallest possible unit of spacetime where the rendering stops being seamless. Physicists have even proposed experiments to test this, like hunting for pixelation in high-energy particle collisions or anomalies in cosmic rays. Whether simulation theory is philosophy's thought experiment or a genuine scientific hypothesis, it forces us to confront the unsettling possibility that the cosmos isn't just stranger than we imagine. It might be stranger than we can imagine, a shadow play cast by minds we'll never meet, in dimensions we'll never see. And if that's true, the biggest mystery isn't whether we're in a simulation, but what or who lies outside it. Imagine a universe that never truly ends, not with a whimper or a bang, but with a whisper that becomes the first breath of a new cosmos. This is the audacious vision of Roger Penrose's conformal cyclic cosmology, a theory where time loops back on itself in an endless dance of cosmic rebirth. At the heart of this idea lies a radical tweak to Einstein's equations. What if the distant future of our universe and the fiery dawn of the next are mathematically the same point? Penrose suggests that as the universe expands into utter emptiness, galaxies burned out, black holes evaporated, particles stretched to near nothingness, it becomes indistinguishable from the infinite uniformity of the Big Bang itself. The end becomes the beginning, not metaphorically but geometrically. But how could dimensions reset in such a cycle? Picture a sheet of paper scrunched into a ball, then smoothed flat again. At the crunch point called a conformal boundary, all distances and times shrink to zero, erasing the past universe's structure while preserving subtle quantum imprints. These imprints, like cosmic graffiti, might carry over into the next cycle, stretching into vast patterns as the new universe inflates. Penrose and his collaborator Vark Gerzadian claim to have found these fingerprints in the cosmic microwave background, strange concentric rings of temperature variation that defy standard inflation theory. These Hawking points, named after Stephen Hawking, could be the evaporated remains of supermassive black holes from a previous universe, their death cries echoing across eternity. Visualizing this cyclical reality is mind-bending. Artists often depict it as a phoenix made of galaxies, each feather a universe rising from the ashes of the last. But the math paints an even stranger picture, a four-dimensional spacetime that, at the conformal boundary, effectively forgets its scale. Distances and durations lose meaning, allowing the infinite future of one cycle to seamlessly become the infinite past of the next. It's as if the universe is a Möbius strip of time, where the flip side is both an ending and a beginning. Critics argue these cosmic microwave anomalies could be statistical flukes or artifacts of how we process the data. Yet if Penrose is right, the implications rewrite not just cosmology but the nature of existence itself. Dimensions wouldn't be fixed scaffolding, they'd be transient, dissolving and reforming with each cycle. The laws of physics might subtly shift between iterations, explaining why our universe seems improbably fine-tuned for life. After all, in an infinite sequence of reboots, even the rarest combinations must eventually arise. What's most haunting is the timescale. Each cycle could last a googol years, long enough for every black hole to evaporate, every proton to decay. From our fleeting human perspective, the cycles are unfathomably vast. But in the grand architecture of reality, they might be as rhythmic as breath. The universe wouldn't just have dimensions, it would become them, over and over, in a loop without beginning or end. And somewhere in that infinite recursion, we're here, in this particular cycle, catching the faintest glimpse of the wheel turning. At the smallest scales imaginable, far smaller than an atom, even tinier than the nucleus inside it, space-time might not be the smooth, continuous fabric we picture. Instead, it could be a turbulent sea of fluctuating dimensions, a fractal frenzy where geometry itself shatters into wild, unpredictable patterns. This is the startling vision of quantum foam, a concept that suggests reality's foundation isn't solid, but frothy and chaotic, bubbling with tiny virtual black holes that wink in and out of existence faster than the blink of an eye. The idea isn't new. Physicist John Wheeler first proposed quantum foam in the 1950s, arguing that at the Planck scale, distances so small they'd make an atom look like a galaxy. The very notions of here and now break down. But it's Carlo Rovelli's loop quantum gravity that gives this foam a startling structure. Imagine space-time not as a blank sheet, but as a network of interconnected loops woven together like an endless cosmic chainmail. These loops aren't fixed, they vibrate and shift, creating a dynamic lattice where dimensions themselves can fluctuate. One moment, a patch of space might behave like 3 dimensions. The next, it could briefly unravel into 2 or even 4, like a piece of fabric fraying at the edges. What does this look like in practice? Think of the froth on a cappuccino. From a distance, it's a smooth surface, but up close, you see bubbles constantly forming and popping. Now imagine those bubbles are microscopic pockets where the rules of dimensionality twist and warp. Matter and energy moving through this foam wouldn't travel in straight lines. They'd stutter and jitter, buffeted by the ever-changing geometry beneath them. That's why some physicists speculate that quantum foam could explain dark energy. The froth's energy might be pushing the universe apart, an invisible pressure woven into the fabric of reality itself. But how would we ever detect such a thing? The fluctuations happen at scales a billion times smaller than anything our instruments can probe directly. However, subtle clues might lurk in the light from distant quasars. If spacetime is truly foamy, high-energy photons traveling across the cosmos should scatter slightly, like light passing through fog. Some observatories, like the Fermi Gamma Ray Space Telescope, hunt for these tiny delays, though so far the evidence remains elusive. The implications are dizzying. If spacetime is fractal and frothy at its core, then dimensions aren't just hidden, they're dancing, flickering in and out of existence with every passing Planck second. Reality isn't a stage, it's a storm, with geometry itself as fleeting as a wave on the ocean. And somewhere in that chaos, the illusion of stability emerges, a universe smooth enough for stars to form, life to evolve, and us to wonder at the hidden whirlwind beneath it all. Imagine if the reason we can't find dark matter, the invisible glue holding galaxies together, isn't because it's hiding, but because it exists in a dimension brushing against ours, just out of reach. This bold idea, known as the AD model after physicists Arconi Hamed, Dimopoulos, and D. Volley, suggests dark matter might be ordinary matter trapped in a parallel universe with extra-spatial dimensions, separated from us by an impassable gulf. Picture 2 sheets of paper floating centimeters apart. You can't touch the other sheet, but if someone tapped it, you might feel the faintest vibration. That's how dark matter could interact with our world, weakly, indirectly, through gravity alone. The math behind this is as elegant as it is strange. In these models, our familiar 3 dimensions are anchored to a brane, while gravity, unlike other forces, can seep into the bulk, the higher dimensional space between branes. Dark matter particles could be stuck on a neighboring brane, invisible to us because light and electromagnetism can't cross the dimensional divide. But their gravitational influence would leak through, explaining why we detect dark matter's pull on galaxies but never see it directly. It's like living next door to a booming concert. You can't see the band, but you feel the bass thrumming through the walls. Experiments at the Large Hadron Collider have hunted for signs of these hidden dimensions by searching for Kaluza-Klein gravitons, particles theorized to briefly tunnel into extra dimensions before snapping back to our brain, carrying telltale energy signatures. If detected, they'd be smoking gun evidence that gravity operates in more than 4 dimensions. Meanwhile, astronomers study anomalies in galaxy rotations and gravitational lensing, looking for patterns that might betray dark matter's higher dimensional origins. One provocative variation suggests dark matter could be mirror matter, an entire duplicate universe identical to ours but offset in higher dimensions, with its own stars, planets, and even life, forever ghostly and unreachable. The chilling implication: we might be the dark matter to them, the unseen force tugging at their galaxies from beyond the dimensional veil. Whether dark matter hides in warped dimensions or shadow branes, the central mystery remains. We're sensing the fingerprints of something vast and invisible, a cosmic neighbor whose existence rewrites the rules of reality. Until we catch a graviton in the act or map gravity's hidden pathways, these dimensions, and the dark matter they might contain, will linger at the edge of our understanding, a tantalizing whisper from the universe's unseen architecture. We've always thought of time as the steady, unshakable fourth dimension, the invisible river carrying everything from past to future. But what if time isn't just one dimension? What if it's a whole spectrum of temporal layers, each folding and twisting in ways that make our linear experience seem like a flat cartoon compared to the richness of reality? This is the mind-bending premise behind theories proposing multiple time dimensions, where causality isn't a straight line but a web of possibilities. Take the block universe theory, for instance. It suggests that past, present, and future aren't sequential, they all exist simultaneously, stacked like pages in a book. Imagine a tesseract, the four-dimensional shadow of a cube. From our limited 3D perspective, we only see slices of it at a time, but in its full form, every moment, your birth, the dinosaur's reign, the heat-death of the universe exists at once, frozen in an unchanging structure. If this is true, our sense of now is just an illusion, a trick of consciousness crawling along one narrow thread of a vast, unchanging tapestry. But why stop at one time dimension? Some models propose two or more, where events could unfold along multiple temporal axes. Picture a sheet of music with melodies moving horizontally and harmonies vertically, except here, the harmonies are alternate timelines branching and intersecting in ways we can't perceive. In such a universe, causality gets messy. An event in one time dimension might influence another unpredictably, like ripples from a stone tossed into a pond crossing paths with ripples from a second stone thrown at a right angle. The implications are staggering. If time has hidden dimensions, free will might not be what we think. Choices could ripple across temporal layers, weaving futures we can't foresee. And if the block universe is real, death loses its finality. Your last breath is just one frame in an eternal reel, forever part of the whole. Scientists probe these ideas through paradoxes. Quantum experiments like delayed choice tests hint that particles might know future measurement settings, as if time's arrow is blurry at the edges. Meanwhile, mathematicians explore geometries where multiple time dimensions don't collapse into chaos but create stable, self-consistent worlds, places where you could, theoretically, travel sideways through time as easily as we move through space. The hardest part, visualizing it. Our brains evolved to navigate 3 spatial dimensions and 1 of time, leaving us blind to the full structure of reality. But every so often, physics gives us a glimpse, a fleeting sense that time, like space, might be far stranger than we ever imagined. And if that's true, the universe isn't just bigger than we thought. It's deeper, richer, and more mysterious in ways we're only beginning to explore. Picture 2 sheets of paper hurtling toward each other in slow motion, except these aren't just sheets, they're colossal multidimensional membranes, entire universes drifting through a hidden dimension. When they collide, the impact doesn't destroy them, it ignites creation itself. This is the heart of the ekpyrotic universe, a radical alternative to the Big Bang, where our cosmos wasn't born from a singularity, but from the clash of higher dimensional worlds. The theory builds on string theory's brane cosmology but adds a dramatic twist. Instead of an explosive beginning, our universe emerged from a cyclical process of cosmic collisions. Imagine 2 branes, each potentially holding its own universe, floating in a higher dimensional space called the bulk. Over eons, they drift closer until gravity pulls them into a cataclysmic crash. The energy of that collision floods our brain, seeding matter, energy, and the very fabric of space-time. But here's the eerie part: the branes don't stick. They rebound, stretching apart again, only to repeat the cycle in a rhythm spanning trillions of years. String gas cosmology offers a variation on this theme. Instead of branes colliding, it proposes that our early universe was a seething tangle of fundamental strings, vibrating filaments of energy, packed into all 9 spatial dimensions predicted by string theory. As these strings interact, they release energy that triggers expansion, but without the need for a singularity. Both theories share a common thread: the Big Bang wasn't a one-time event. It was a phase in an endless cosmic dance with hidden dimensions orchestrating the steps. Now, slow that collision down to human scales. As the branes approach, quantum fluctuations, tiny ripples in their surfaces get stretched across the cosmos by the impact. These ripples become the seeds for galaxies, etched into the newborn universe like fingerprints. The process explains the cosmic microwave background's eerie uniformity without requiring rapid inflation because the branes were nearly identical before colliding. Their energy spread evenly from the start. Critics argue that without inflation's exponential stretching, the ekpyrotic model struggles to explain certain large-scale structures. Supporters counter that brane collisions naturally generate the right patterns, and they point to potential imprints in the cosmic microwave background anomalies that could betray a pre-Big Bang phase. Meanwhile, string gas cosmology suggests its own signatures, unique patterns of gravitational waves from the early universe's tangled strings, which future observatories might detect. The implications are staggering. If the ekpyrotic universe is right, our cosmos isn't just one chapter in a story, it's a single page in an endless book, with each collision rewriting reality. And those hidden dimensions, they're not just mathematical abstractions, they're the stage where the most titanic events in existence unfold, unseen yet undeniable. Whether through colliding branes or vibrating strings, these theories force us to confront a humbling truth. Our universe might not have started with a bang, but with a whisper from a dimension we can't even see. At the moment of the Big Bang, when the universe was hotter and denser than the core of a star, something bizarre might have happened to the very fabric of reality. Its dimensions began to melt away. This isn't science fiction, it's a serious hypothesis called vanishing dimensions, which suggests that under extreme energy conditions, space itself simplifies, collapsing from our familiar 3 dimensions down to just 2. Imagine stepping into a black and white movie where depth disappears and everything flattens into silhouettes. Now picture that happening to the universe itself, but in reverse. As you rewind toward the Big Bang, the 3rd dimension evaporates like mist in sunlight, leaving only length, width, and time. Why would dimensions vanish? The answer lies in quantum gravity, the holy grail of physics. At the universe's birth, energies were so intense that gravity and quantum mechanics, normally operating at vastly different scales, were forced to interact. But combining them mathematically is like trying to mix oil and water. Some theorists propose that reducing dimensions could resolve this clash. In a 2-dimensional high-energy state, gravity's equations simplify dramatically, sidestepping the infinities that plague traditional models. It's as if the universe, faced with an impossible calculation, cheated by erasing complexity until the math worked. This idea isn't just speculative. Observations of cosmic rays high-energy particles from deep space show anomalies that could hint at dimensional shifts. At energies approaching the Planck scale, particles behave as if they're moving through fewer dimensions, like marbles rolling across a table instead of tumbling through a room. Even black holes, those cosmic shredders of spacetime, might remember this flattened past. Their entropy, a measure of disorder, aligns suspiciously well with 2-dimensional models, as if the 3rd dimension is an afterthought stitched in later. Visualizing this isn't easy. Think of reality as a sheet of paper crumpling under heat. As temperatures rise, the creases smooth out, leaving a flat surface. But here's the twist: time remains untouched. So while space collapses to 2 dimensions, time keeps flowing, creating a bizarre hybrid where the laws of physics rewrite themselves. Matter in this state wouldn't behave like anything we know. Particles might vibrate in impossible ways. Forces could unify effortlessly, and the concept of distance might lose all meaning. The implications ripple far beyond the Big Bang. If dimensions emerge as the universe cools, could they disappear again under extreme conditions? Some models suggest that in the heart of a black hole or during high-energy particle collisions, spacetime might locally forget a dimension, creating fleeting pockets where physics goes haywire.
Experiments at the Large Hadron Collider hunt for these glitches like shadows cast by a collapsing dimension. And if they're found, it would mean our reality isn't just hiding dimensions, it's shedding them, adapting like a chameleon to the universe's most violent moments. What's most unsettling is the question it forces us to ask: are dimensions fundamental or just emergent features, flickering into existence when the energy is right? If the latter, then the three-dimensional world we take for granted might be nothing more than a cosmic phase as transient as ice melting into water. And somewhere, in the searing heat of the early universe or the crushing depths of a singularity, reality might still be playing by simpler, stranger rules written in a language of two dimensions waiting to be decoded. What if consciousness isn't just a byproduct of the brain, but a bridge to dimensions beyond our perception? This wild idea isn't just New Age speculation. It's rooted in serious scientific theories like ORCH, or proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. They argue that consciousness arises from quantum vibrations in microtubules, tiny structures inside neurons. But here's the twist: these quantum processes might not be confined to our three-dimensional world. Instead, they could be tapping into a deeper, more complex dimensional framework, like ripples spreading into an unseen pond. Think of your brain as a radio receiver. The music you hear doesn't originate inside the radio. It's plucked from invisible waves all around you. ORCH, or suggests consciousness, works similarly, with microtubules acting as quantum antennas tuned into higher dimensional reality. When these vibrations reach a critical threshold, what Penrose calls objective reduction, they collapse into definite states, creating moments of awareness. But the real magic happens in the collapse itself, which might momentarily open a doorway to geometries beyond spacetime, allowing information to flow from dimensions we can't ordinarily access. Skeptics, of course, aren't convinced. Critics point out that the brain is too warm and noisy for delicate quantum effects to survive without disruption. They argue classical neuroscience explains consciousness just fine without invoking extra dimensions. But supporters counter with examples like psychedelic experiences, where people report sensations of infinite connectivity, time dilation, or encounters with seemingly interdimensional entities. Could these be glimpses into the higher dimensional substrate ORCH describes? Studies on DMT, a powerful psychedelic, show brain activity decreasing during intense trips, the opposite of what you'd expect if these visions were mere neural noise. The debate gets even stranger when you consider near-death experiences. Patients clinically dead for minutes sometimes return with detailed recollections of floating outside their bodies or moving through tunnels of light, accounts that eerily mirror descriptions of higher dimensional travel in theoretical physics. If consciousness can detach from the brain, even temporarily, where does it go? Some theorists propose it slips into the bulk, the hidden dimensional space of brain cosmology, experiencing reality unfiltered by our limited sensory apparatus. Alternative theories offer their own spin. Integrated information theory, for instance, treats consciousness as a property of any sufficiently complex system, from brains to computers, but leaves the door open for exotic physics. Meanwhile, panpsychists suggest consciousness might be fundamental to the universe itself, woven into the fabric of spacetime like gravity. If that's true, then higher dimensions wouldn't just host consciousness, they might be conscious in ways we can't begin to fathom. Whether ORCH holds up or not, the larger question lingers. Could our minds be the one tool capable of perceiving dimensions science can't yet measure? After all, we've always trusted our senses to map reality. But if those senses are just decoding a narrow slice of the cosmos, what wonders might be flourishing in the shadows, just beyond the reach of our instruments, yet whispered to us in dreams, visions, and the quietest corners of thought? Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity wins, crushing matter into oblivion. But what if these monstrous voids aren't just dead ends?
What if they're doorways, warping space-time so violently that they tear open passages to dimensions beyond our own? This is the heart of the four-dimensional black hole hypothesis, an idea that bends the rules of reality itself. Picture a black hole not as a pit, but as a whirlpool in a higher dimensional ocean, its funnel stretching into realms we can't see. The math behind this is as elegant as it is strange. Einstein's equations allow for bridges called Einstein-Rosen bridges, wormholes linking distant points in spacetime. But string theory takes it further, suggesting black holes might be shadows of higher dimensional objects, like a three-dimensional imprint of a four-dimensional storm. At the event horizon, the point of no return, things get even weirder. Quantum mechanics predicts a nightmarish scenario called the firewall paradox, where an invisible wall of searing radiation vaporizes anything crossing it. This clashes violently with relativity, which insists you'd pass through unharmed, at least until spaghettification kicks in. But here's where holographic duality offers a way out. It suggests the firewall isn't a physical barrier, but a computational one, a glitch in how information is encoded at the boundary between our universe and whatever lies beyond. Imagine a corrupted file on the edge of a hard drive. The data isn't lost, just scrambled into chaos. Then there's ER equals EPR, a radical proposal by physicists Juan Maldaisner and Leonard Susskind. They argue that entangled particles, those spookily connected across vast distances, might be linked by microscopic wormholes threading through higher dimensions like invisible stitches in spacetime. If true, every quantum connection could be a tiny black hole in disguise, a hidden tunnel through the bulk of reality. This would mean the universe isn't just filled with black holes, it's woven by them, with entanglement and gravity, two sides of the same cosmic coin. Visualizing this isn't easy. Think of a black hole's singularity not as a dot, but as a membrane, vibrating in higher dimensions like a drumhead struck by invisible hands. Some models suggest these vibrations could birth entirely new universes, bubbling out of the collapse like soap bubbles from a wand. Others propose that what we call a singularity might be a flaw in our math, a sign that we're missing a dimension where the equations smooth out. The most tantalizing clue: Hawking radiation. If black holes leak particles over time, those particles might carry fingerprints of the higher dimensional landscape they escaped from. Future telescopes tuned to the faintest whispers of dying black holes could detect anomalies, patterns in the radiation that betray extra dimensions curling just beyond reach. Until then, these ideas linger at the edge of physics, too compelling to ignore, too wild to confirm. One thing's certain: if black holes are gateways, they're the most forbidding ones imaginable, locked by gravity's might and encoded in quantum riddles we've only begun to decipher. Imagine two coins flipped on opposite sides of the universe. No matter how far apart they are, they always land matching heads or tails instantly, defying the speed of light. This eerie connection is quantum entanglement, one of physics' most baffling phenomena. But what if the secret behind this spooky action at a distance isn't just weird, it's dimensional? Some theorists propose that entangled particles aren't truly separate at all. They're tethered through hidden folds in spacetime, like ants crawling on opposite sides of a folded piece of paper, unaware they're inches apart in a third dimension. The math behind this is as elegant as it is mind-bending. Einstein's equations allow for shortcuts through spacetime called wormholes, tunnels linking distant points in an instant. Now imagine these wormholes aren't cosmic-scale structures, but microscopic threads woven into the fabric of reality, connecting entangled particles through higher dimensions we can't perceive. This AR equals EPR conjecture, coined by physicists Juan Maldaisner and Leonard Susskind, suggests that entanglement and wormholes are two descriptions of the same underlying geometry. When particles become entangled, they might be stitching a tiny wormhole between them, a thread so fine it exists only in the quantum foam of spacetime. Visualizing this requires a shift in perspective. Think of space-time not as a flat sheet but as a loaf of bread, with each slice representing a three-dimensional moment. Now picture two raisins embedded in the loaf, entangled particles connected not through the bread surface but by a tunnel burrowing straight through the dough. From within any single slice, the raisins appear separate, but the hidden tunnel makes their synchronized behavior inevitable. This could explain why measuring one particle instantly affects its partner. They're not signaling faster than light, they're already linked through a higher dimensional backdoor. The implications ripple far beyond theory. If entanglement relies on extra dimensions, it might explain why quantum mechanics and gravity, the two great pillars of physics, have resisted unification. Gravity could be the cumulative effect of countless microscopic wormholes threading through higher dimensional space, while quantum effects like entanglement emerge from these same hidden connections. Experiments with entangled photons already show correlations that classical physics can't explain, and some physicists speculate that subtle anomalies in these results, tiny deviations from perfect synchronization, could hint at the shape of these extra dimensions, like echoes bouncing off unseen walls. Critics argue that wormhole-based entanglement is still speculative, lacking direct experimental proof, but supporters point to the AD/S/CFT correspondence, a mathematical framework where a higher dimensional wormhole is perfectly equivalent to entangled particles in a lower dimensional world. It's as if the universe offers two languages, one describing geometry, the other describing quantum fields, and they're telling the same story. Future quantum gravity experiments might hunt for signatures of these hidden tunnels, like gravitational disturbances too faint for current detectors or patterns in particle collisions that betray unseen dimensional pathways. The strangest possibility: if entanglement is truly a dimensional phenomenon, then every quantum connection in the universe, from lab experiments to the bonds between atoms in your body, might be part of a vast, invisible network, a higher dimensional web humming beneath the surface of reality. Particles we think of as isolated could be holding hands across dimensions we'll never see, weaving the cosmos together in ways we're only beginning to glimpse. And if that's true, then the true nature of reality isn't just hidden, it's folded, pleated, and stitched together by threads we're just learning to trace. If the hidden dimensions of string theory exist, they can't be just any random shapes. They have to be exquisitely precise mathematical forms called Calabi-Yau manifolds. Picture a snowflake, but one sculpted in 6 dimensions, with folds and curves so intricate that no two Calabi-Yau shapes are exactly alike. These structures aren't just abstract art, they're the DNA of reality itself, determining everything from the mass of an electron to why gravity is so weak compared to other forces. Why these specific shapes? The answer lies in supersymmetry, the idea that every known particle has a heavier, unseen twin. For string theory's equations to balance, the extra dimensions must satisfy a laundry list of geometric conditions. They have to be Ricci flat, meaning no intrinsic curvature, and compact enough to curl up smaller than an atom. Calabi-Yau manifolds fit the bill perfectly, their labyrinthine geometry providing exact mathematical pathways for strings to vibrate without breaking the rules of quantum mechanics. The consequences of these shapes are staggering. A string vibrating in one Calabi-Yau pocket might become an electron, while the same string dancing through a different fold emerges as a photon. The number of holes, like donut-like loops in the manifold, directly influences how many generations of particles exist. 3 holes, you get 3 families of quarks and leptons, just like we observe. Change the holes and suddenly protons might not form, or atoms could dissolve instantly. It's as if the universe is a lock, and Calabi-Yau shapes are the only keys that fit. Visualizing these manifolds pushes even mathematicians to their limits. While we can't see 6 dimensions, we can project them into 3, like flattening a globe into a map. The resulting forms resemble twisted knots, intricate lattices, or alien coral reefs, each one a universe of possibility. Some have sharp, angular symmetries, others flow with organic curves. But what's truly mind-bending is that these shapes aren't static. Quantum fluctuations could make them writhe and pulse, altering the laws of physics in ways we can't predict. Future particle colliders might look for echoes of these hidden geometries. If supersymmetric particles are discovered, their properties could hint at the specific Calabi-Yau structure our universe chose. Until then, these shapes remain hypothetical masterpieces, silent architects of reality, folding and unfolding in dimensions we'll never see, yet governing every quark, every star, every breath we take in the visible world. Nikola Tesla once claimed that if you understood the significance of the numbers 3, 6, and 9, you'd hold the key to the universe. While dismissed as eccentricity in his time, modern physics is uncovering something startling. Those numbers might hint at hidden dimensions pulsing beneath reality's surface, vibrating at frequencies we can't perceive but that shape everything from atoms to galaxies. This is the tantalizing premise of dimensional resonance theory, the idea that higher dimensions don't just exist, they sing. They're oscillations influencing matter in ways we're only beginning to decode. Picture a guitar string, pluck it, and it vibrates at specific frequencies, creating distinct musical notes. Now imagine that string isn't just a one-dimensional thread, but a loop whirling through 6, 7, or even 11 dimensions. The vibrations it produces wouldn't just create sound, they'd define the very fabric of particles and forces. In string theory, this isn't metaphor, it's the foundation of reality. An electron might be a string vibrating at one frequency, while a quark hums at another, all orchestrated by the hidden geometry of Calabi-Yau manifolds. But what if these vibrations extend beyond quantum scales? What if entire dimensions resonate, their standing waves echoing through the cosmos like a cosmic tuning fork? Tesla's obsession with vibration wasn't just about electricity. He speculated that certain frequencies could unlock hidden energies or even bend space-time, ideas that now find eerie parallels in modern physics. When researchers model higher dimensional spaces, they find stable configurations often rely on harmonic resonance, where waves reinforce rather than cancel each other. These aren't abstract calculations, they could explain real-world anomalies. Some physicists propose that dark matter's elusive nature stems from particles vibrating out of phase with our dimension, like a radio station broadcasting just outside your receiver's range. Others suggest gravitational waves, ripples in space-time, might carry imprints of higher dimensional harmonics, detectable as faint glitches in future interferometers. The numbers 3, 6, and 9 resurface here in surprising ways. In certain string theory models, stable vibrations require symmetries divisible by these integers, a mathematical echo of Tesla's mystical assertions. Even more compelling, when physicists simulate higher dimensional standing waves, patterns emerge resembling sacred geometries found in ancient art, from the flower of life to the Sri Yantra. Coincidence, perhaps, but the unsettling truth remains. If dimensions vibrate, their frequencies might be written into the fabric of existence itself, from the spin of electrons to the orbits of planets. Experiments are already hunting for these hidden rhythms. Crystals subjected to extreme pressures exhibit frequency locking, where atomic vibrations suddenly sync with unexplained external patterns. Some labs report anomalies in high-energy particle collisions, brief energy spikes that match no known particle, as if something else momentarily resonated with our dimension. Even black holes might hold clues. Their mergers emit gravitational waves with overtones that, according to some models, could encode information about extra dimensions, like a bell's ring revealing its shape. The implications are profound. If dimensional resonance is real, tuning into these vibrations could revolutionize energy, computation, even our understanding of consciousness. Imagine devices that harness higher dimensional harmonics, or materials engineered to vibrate in sync with hidden layers of reality. More hauntingly, it suggests the universe isn't just a static stage, it's a dynamic, humming entity, its dimensions thrumming with energies we're only beginning to sense. Tesla might have been closer to the truth than anyone guessed. The key to the cosmos wasn't in brute force or sheer size, but in listening, really listening, to the hidden music of the dimensions themselves. Think of the Higgs field as the cosmic glue holding reality together. Without it, particles would whiz around at light speed, never clumping into atoms, stars, or us. But what if this same field does something even stranger, acting as a bouncer at the universe's dimensional nightclub, letting some dimensions thrive while collapsing others into oblivion? Here's the wild idea: the Higgs mechanism might not just give particles mass, it could be the reason we experience exactly 3 spatial dimensions instead of 2 or 5 or 20. Picture the early universe as a boiling pot of spaghetti, with dimensions tangled in every direction. As it cooled, the Higgs field condensed like droplets on a cold window, its energy settling into the lowest possible state. But this wasn't uniform. Some dimensions, like our familiar 3, stabilized, while others crumpled like paper in a fist, squeezed into microscopic loops by the Higgs influence. It's as if the universe played a game of musical chairs, and when the Higgs field sat down, only certain dimensions found a seat. The rest were left standing, curled up too tightly for us to notice. This isn't just speculation. The math suggests that in higher dimensional theories, the Higgs field's vacuum expectation value, a fancy term for its default energy level, could determine which dimensions stay spacious and which get crushed. Imagine blowing up a balloon inside a shoebox. The balloon, our 3 dimensions, expands to fill the space, while the remaining gaps, extra dimensions, are pinched into corners. The Higgs field might be that pressure shaping the geometry of reality itself, but there's a terrifying twist: vacuum decay. The Higgs field's current state isn't necessarily the lowest possible energy level. It might be metastable, like a pencil balanced on its tip. A nudge, whether from quantum fluctuations or some high-energy event, could send it tumbling into a truer, deeper vacuum. If that happens, the Higgs field's value would shift, potentially rewriting the rules of dimensionality in a catastrophic chain reaction. It wouldn't just collapse hidden dimensions, it might unravel ours, rewriting physics in a propagating bubble of destruction. Visualize this like a bubble chamber experiment where particles leave trails in superheated liquid. Now imagine the entire universe as that liquid, and the bubble is a region where the Higgs field decays, expanding at light speed. Inside, dimensions might reconfigure, atoms disintegrate, and the very concept of space as we know it dissolves. The good news: if such a bubble formed, we'd never see it coming. The bad news: it could already be on its way from some distant galaxy, a silent tsunami of existential erasure. The Higgs field, then, isn't just a backdrop, it's an active architect, sculpting dimensions while teetering on a knife's edge. And if we're lucky, its current configuration is stable enough to last billions of years. But if not, well, the universe might have more surprises in store, lurking in the quantum shadows where dimensions are born and die. Long before telescopes or particle colliders, ancient mystics and scholars were already grappling with the idea of hidden dimensions, encoding them in sacred geometry, allegory, and intricate cosmological maps. Take the Kabbalah's Tree of Life, a mesmerizing diagram of 10 interconnected spheres called Sephirot. At first glance, it's a spiritual blueprint for divine energy. But look closer, the Sephirot aren't just symbols, they're described as vibrating dimensions of existence, layered realities where each world operates under different physical and metaphysical laws. The lowest, Malkuth, represents our tangible universe, while higher realms like Binah and Chokmah hint at abstract, hyperdimensional spaces where time and form dissolve. The parallels to modern physics are uncanny, like a pre-scientific echo of Calabi-Yau manifolds, where each folded dimension influences the others in a delicate, interdependent dance. Hindu cosmology pushes the vision even further. The Puranas describe universes stacked like lotus petals, each with its own laws and timelines, floating in an infinite ocean of causal waters. The Vishnu Purana specifically mentions Turiya, a state beyond the three familiar dimensions, a fourth spatial realm inaccessible to ordinary perception. Even more striking are the descriptions of lokas and talas, realms of existence that coexist with our own but vibrate at different frequencies, making them invisible without spiritual or technological transcendence. It's as if ancient seers intuited the concept of brain worlds millennia before physicists coined the term, envisioning parallel realities separated not by distance but by dimensional phase. The evidence isn't just textual. Medieval Islamic scholars like Al-Hazan and Avicenna drew elaborate geometric diagrams of nested cubes and spirals, attempting to map the hidden architecture of creation. The Vedas' Shri Yantra, a complex interlocking of triangles, encodes mathematical ratios that mirror modern theories of dimensional compactification. And then there's the enigmatic emerald tablet of Hermes Trismegistus, which declares, "as above, so below," a cryptic nod to holographic principles or dimensional symmetry long before Leibniz or Einstein. These weren't mere myths, they were rigorous attempts to document a reality beyond sensory limits, using the language of their time. What's haunting is how these traditions converge with cutting-edge physics. The Kabbalistic concept of tzimtzum, divine contraction to make space for creation, resembles the inflationary epoch of the Big Bang, where space-time expanded exponentially to allow structure to form. Hindu texts speak of cyclical universes collapsing and reborn, eerily mirroring Penrose's conformal cyclic cosmology. Even the Mayan calendar's fifth world hints at a transition into higher dimensional awareness, a theme that resurfaces in modern theories like the holographic universe. Were these cultures merely guessing, or did they access insights through meditation, ritual, or lost technologies that let them perceive dimension science is only now rediscovering? The clash between skepticism and wonder here is palpable. Critics argue these parallels are coincidental, that ancient symbols are too vague to map onto precise mathematical models. But the counterargument is just as compelling. When multiple disconnected traditions from the Jewish Kabbalah to the Buddhist mandala independently describe layered dimensions and vibrational realities, it's harder to dismiss as fantasy. Perhaps the true lesson lies in humility. Modern physics, for all its equations and colliders, might be retracing steps first walked by mystics who saw the universe not through microscopes but through the lens of transcendent experience. Whether their visions were literal or metaphorical, one thing's clear: the human fascination with hidden dimensions isn't a new obsession. It's an ancient whisper passed down through millennia, now finding its voice in the equations of a new age. What if the universe isn't just described by mathematics? What if it is mathematics, not merely a system we invented to decode reality, but reality itself, with every star, atom, and hidden dimension nothing more than an equation made manifest? This is the spine-tingling premise of Max Tegmark's mathematical universe hypothesis, a theory so radical it erases the line between abstraction and existence. Imagine every possible mathematical structure, every shape, every symmetry, every conceivable configuration of numbers and dimensions, not as ideas floating in a mathematician's mind, but as actual physical universes. Somewhere in this infinite library of equations, one particular set describes our cosmos with its three spatial dimensions and quantum quirks. But turn the page and you'll find others. Universes with 7 dimensions where circles have corners, or fractal realities where time branches like a never-ending tree. The implications explode conventional thinking. If the hypothesis holds, then every mathematically consistent universe must exist. There's no creator, no cosmic dice roller, just the cold, beautiful inevitability of logic. Tegmark divides this multiverse into 4 levels, each more mind-bending than the last. Level 1, infinite versions of our own universe scattered across space. Level 2, bubble universes with different physical constants, but it's Level 4, the mathematical universe, that shatters expectations. Here, reality isn't governed by math, it is math. A triangle isn't a representation of three connected lines. It's the three-dimensional shadow of an equation living in a higher dimensional space. Critics push back hard. Philosophers argue that confusing mathematical models with physical reality commits the unreasonable effectiveness fallacy. Just because math describes the universe well doesn't mean they're identical. Others counter that some mathematical structures are inherently paradoxical. What would a universe built on an unsolvable equation look like? But Tegmark's defenders point to quantum mechanics, where particles exist in superpositions until observed. Could this indeterminacy reflect deeper mathematical truths, where every possible outcome must play out in some structure? Visualizing this is like trying to dream in 4 dimensions. Picture a fractal where zooming in reveals ever more intricate patterns, each layer its own self-contained universe. Some branches might host life, others could be barren wastelands of pure geometry. The eerie part, we're confined to one tiny slice of this fractal, our perception limited by the dimensions our particular equation allows, those hidden dimensions we've been chasing. They might not be curled up, they could simply belong to other mathematical structures forever beyond our reach. The debate forces a profound question: is mathematics discovered or invented? Ancient philosophers like Pythagoras believed numbers were divine, woven into the fabric of existence. Modern physicists often treat math as a tool. Tegmark's hypothesis splits the difference. It suggests the tool is the fabric. If he's right, then every time a mathematician scribbles an equation, they're not just exploring an idea, they're charting territory in a landscape of real, tangible worlds. The universe isn't written in the language of math, it is the language whispering its secrets in a code we're only beginning to crack. Gravity already bends the fabric of space-time like a bowling ball on a trampoline, but what if black holes and other cosmic monsters don't just warp dimensions, they unzip them? At the very edge of a singularity, where gravity becomes so intense that even light surrenders, the familiar rules of reality might start to fray. Space-time could stretch like cosmic taffy, thinning until hidden dimensions usually coiled tighter than a watch spring begin to peek through. This isn't just poetic speculation. The equations of general relativity break down at singularities, screaming that something radical must happen, and extra dimensions could be the universe's escape hatch from mathematical oblivion. Picture a black hole's event horizon not as a smooth boundary, but as a turbulent quantum storm. Here, virtual particles pop in and out of existence, some escaping as Hawking radiation. But deeper in, near the singularity itself, space-time may undergo dimensional phase transitions like water freezing into ice, except the ice is a lower dimensional state where time and space behave unpredictably. Some models suggest gravity could momentarily leak into these exposed dimensions, weakening just enough to leave fingerprints in the ripples of colliding black holes. That's where LIGO, the Laser Interferometer Gravitational Wave Observatory, becomes a dimensional detective. Every time it detects gravitational waves, the cosmic aftershocks of black hole mergers, it's potentially recording more than just space-time vibrations. Hidden within those faint chirps could be anomalies, tiny deviations from Einstein's predictions that betray gravity's secret dalliances with extra dimensions. The math behind this is as elegant as it is unsettling. In higher dimensional theories, gravity's strength isn't constant, it varies with the energy and scale of the system. Near a singularity, energies reach such extremes that the gravitational force might momentarily remember its full multidimensional nature, like a compressed spring suddenly released. LIGO precise measurements could catch this as a subtle mismatch in the waveforms, a hiccup in how the black hole's in-spiral matches theoretical templates. Future upgrades to LIGO or space-based detectors like LISA might even spot echoes in the gravitational wave signals, reverberations caused by gravity bouncing off hidden dimensional barriers near the event horizon, like sound waves in a cavernous hall. Not all physicists are convinced. Critics argue these effects could be buried under noise or explained by mundane astrophysical processes. Yet the hunt continues because the payoff would be revolutionary. If dimensional shifts near singularities are real, they'd rewrite our understanding of black holes from cosmic trash compactors to dimensional portals, places where the universe's deepest architecture is stretched, tested, and perhaps even glimpsed. Every collision LIGO hears might carry whispers from realms beyond our perception, encrypted in the language of gravity's song. And if we learn to decode them, we might finally answer one of physics' oldest questions: what truly happens in the heart of darkness? John Wheeler, the visionary physicist who coined the term black hole, once proposed an idea so radical it redefined our place in the cosmos. The universe might not just exist, it might require us to observe it into being. This participatory universe hypothesis suggests that dimensions themselves could remain fluid and undefined until consciousness pins them down, like a painter deciding where to place brushstrokes on a blank canvas. Picture the double-slit experiment, that cornerstone of quantum weirdness. When unobserved, particles act as waves, slipping through both slits simultaneously, a behavior impossible in our familiar three-dimensional world. But the moment you set up a detector to watch, the wave collapses into a single, definite path. Now stretch that logic across the fabric of reality. What if entire dimensions behave like those quantum particles, shimmering possibilities that only solidify when observed? This isn't just philosophy. Quantum decoherence, the process by which quantum superpositions dissolve into classical certainty, offers a potential mechanism. Every interaction with the environment acts like an unconscious observation, chiseling fuzzy probabilities into concrete reality. Apply this to dimensions and you get a startling vision. The three spatial dimensions we experience might be the ones that decode first, stabilized by countless quantum observations from particles bumping into each other in the early universe. Meanwhile, other dimensions could have remained collapsed, coiled into microscopic loops, not because they're inherently small, but because nothing ever observed them into full existence. Visualizing this is like imagining a room filled with faint, shifting shadows. Only when you shine a light when observation occurs do some shadows snap into sharp relief as objects, while others vanish entirely. In this view, dimensions aren't fixed scaffolding. They're a spectrum of possibilities, with consciousness or even simple interactions acting as the filter that selects which ones become real. The eerie implication: there might be corners of the cosmos where different dimensional configurations dominate, regions where quantum systems haven't fully decoded, and the very structure of space remains unsettled. Critics argue this veers dangerously close to solipsism, the idea that reality exists only in the mind. But Wheeler's insight was subtler. He saw observation not as human-centric, but as a fundamental feature of physical law. Even a single photon hitting a dust grain could count as an observation capable of collapsing possibilities. The double-slit experiment, then, becomes more than a quantum quirk. It's a microcosm of how dimensionality itself might emerge from a sea of potentials. Future experiments could test this. Ultra-cold quantum systems, isolated from environmental noise, might reveal whether dimensional properties fluctuate when unobserved. Some theorists even speculate that the cosmic microwave background, the afterglow of the Big Bang, could bear imprints of early dimensional decoherence, subtle patterns betraying the moment our universe chose its spatial architecture. Until then, Wheeler's hypothesis lingers as both challenge and invitation to consider that the dimensions we call home might not be the only ones possible, just the ones we've collectively observed into being. And in the unlit corners of the cosmos, who knows what other geometries might still be waiting, trembling between existence and oblivion. Forget gravity as the universe's primary architect. What if the true sculptor of cosmic structures isn't curved space-time, but crackling electromagnetic forces dancing through interstellar plasma? Plasma cosmology challenges mainstream physics with a radically different vision. That the universe isn't just threaded with hidden dimensions, but electrified filaments spanning light, gears, structures so vast they might be shadows of higher dimensional currents we can't yet measure. At the heart of this theory lies the work of Christian Birkeland, a Norwegian scientist who, over a century ago, discovered Earth's auroras were powered by charged particles flowing along magnetic field line streams now called Birkeland currents. Today, plasma cosmologists argue these currents don't just light up polar skies, they weave the cosmos itself into a web of glowing filaments, sculpting galaxies and galaxy clusters like beads on an invisible string. The implications for hidden dimensions are startling. In mainstream string theory, extra dimensions curl up at microscopic scales. But plasma cosmology suggests large-scale electromagnetic phenomena might reveal higher dimensions through their geometry. Computer simulations of plasma behavior in 3 dimensions produce flat, sheet-like structures, nothing like the twisted cosmic filaments we observe. Yet when researchers model plasma in hypothetical higher dimensional spaces, the swirling charged particles spontaneously form intricate filamentary networks eerily resembling the cosmic web mapped by modern telescopes. It's as if the universe is tracing the edges of dimensions we can't see, with glowing plasma acting as multidimensional ink. Now zoom out to the largest scales. The observed universe shows galaxies clustered along vast, thread-like structures stretching hundreds of millions of light-years. A pattern shockingly similar to laboratory plasma discharge experiments scaled up by 50 orders of magnitude. Mainstream cosmology attributes these filaments to dark matter's gravitational pull, but plasma physicists counter that electromagnetic forces in ionized gas could achieve the same structures without invisible matter through self-organizing Z-pinch effects where parallel currents spiral together. The most compelling evidence, many cosmic filaments like the mysterious Hand of God nebula glow with synchrotron radiation, a telltale signature of electrons spiraling through magnetic fields. The controversy cuts deep. Mainstream astrophysicists argue plasma lacks the power to shape the universe without gravity's dominance. Yet plasma cosmology's proponents point to unexplained phenomena like the axis of evil, a bizarre alignment of cosmic microwave background anomalies stretching across space, which some suggest could mark the imprint of a gargantuan Birkeland current. Others study void filaments, mysterious tendrils of galaxies surrounding empty cosmic voids, whose precise alignment defies gravitational simulations but matches plasma instability patterns. The most radical idea, these plasma filaments might not just occupy our 3 dimensions, they could be higher dimensional circuits. Some models propose that what we perceive as separate galactic clusters are actually interconnected through electromagnetic vortices in hidden dimensions, like beads on a necklace dipping in and out of a folded tablecloth. Future radio telescopes like the Square Kilometre Array could test this by mapping the magnetic fields threading the cosmic web, hunting for coherence patterns that betray underlying higher dimensional geometry. Whether plasma cosmology ultimately rewrites astrophysics or not, its filamentary vision offers something profound, a reminder that the universe's hidden architecture might not just hide in quantum foam or curled-up strings. It could be written in the electric fire stitching the cosmos together, visible to anyone daring to look. Long before physicists scribbled equations about wormholes, our ancestors were already dreaming of bridges between worlds, mythic passages woven from starlight, fire, and divine craftsmanship. Take the Bifrost of Norse legend, that shimmering rainbow bridge linking Midgard, the realm of humans, to Asgard, home of the gods. Described as burning with 3 colors yet impossibly strong, It wasn't just a symbol, it was a literal highway between dimensions, guarded by the watchful god Heimdall. Modern cosmology offers an uncanny parallel, traversable wormholes, theoretical tunnels through space-time stabilized by exotic matter, the Bifrost tri-colored flames. Perhaps a poetic rendering of the gravitational lensing and quantum flares that might adorn a real dimensional gateway. Then there's Jacob's ladder from the Hebrew Bible, a staircase stretching from earth to heaven, with angels ascending and descending. Jewish mysticism later interpreted it as a conduit for divine energy, a channel between finite and infinite realms. String theory's brain-world scenarios echo this eerily: our universe as one membrane, heaven as another, connected by a higher dimensional bulk that permits travel between them. Even the angels' rhythmic movement aligns with modern hypotheses about cyclic universes or particles tunneling through extra dimensions. The parallels aren't coincidental, they're glimpses of an intuitive understanding that predates telescopes by millennia. Indigenous traditions add another layer. The Aboriginal peoples of Australia speak of the dream time, a multidimensional landscape where ancestors sculpted the world by singing it into existence. The Yoruba of West Africa describe Oran, a parallel realm accessible through sacred groves and rituals. These aren't mere metaphors but sophisticated cosmologies suggesting that dimensional boundaries are permeable, woven into the fabric of cultural memory. Modern sci-fi art often visually echoes these myths. Alex Gray's psychedelic portraits of interdimensional beings, for instance, or the Stargate franchise's ringed portals, which mirror descriptions of Celtic fairy mounds or Hindu vimanas, flying chariots said to traverse cosmic planes. What's striking is how these myths converge on details that science now takes seriously. The Bifrost was said to burn away unworthy travelers, a poetic analog to the spaghettification and Hawking radiation that would doom anyone entering an unstable wormhole. Jacob's ladder's angels moved in both directions, hinting at the time-symmetric nature of quantum entanglement. Even the Dreamtime's nonlinear chronology mirrors physicists' musings about block time or Penrose's cyclic universes. The difference: where myths used symbolism, science uses tensors and wave functions, but the underlying intuition remains startlingly similar. Today, artists and theorists collaborate to reinterpret these ancient visions. Digital illustrations overlay the Bifrost with gravitational lensing effects, its rainbow arcs bending like space-time around a black hole. Concept art for Jacob's ladder depicts it as a DNA-like double helix of light, evoking string theory's vibrating filaments. These aren't just creative flights, they're bridges between worlds, much like the myths themselves, reminders that the human imagination has always sensed dimensions beyond the visible, long before the math caught up. Whether through sacred stories or quantum equations, the message is the same. The universe is vaster, weirder, and more connected than it seems, with gateways waiting in the spaces between what we know and what we've yet to discover. We've spent centuries thinking of dimensions as spatial length, width, height, or temporal, like the steady tick of a clock. But what if there's another layer to reality, one made not of matter or energy, but of pure information? This is the radical proposition of digital physics, a theory that reimagines the universe as a computational system, where every particle, every force, every flicker of light is fundamentally data. Claude Shannon, the father of information theory, laid the groundwork by showing that information isn't just about words or numbers. It's a measurable quantity like mass or charge with its own physics. Extend that idea to its limit and you arrive at a staggering possibility. Information might not just describe reality, it could be reality with its own hidden dimension weaving through the fabric of existence. Picture the universe as a vast, dynamic network where every interaction, from the collision of galaxies to the firing of a neuron, is a transfer of information. In this view, space-time isn't the stage. It's the output of deeper informational processes, like the 3D world rendered by a video game engine running on binary code. Black holes throw this into sharp relief. According to quantum mechanics, information can never be destroyed, yet black holes seem to violate this by swallowing particles and leaving no trace. The infamous black hole information paradox has physicists like Stephen Hawking and Leonard Susskind at odds, but digital physics offers a wild solution. The information isn't lost. It's encoded on the event horizon's surface, a two-dimensional holographic projection of the three-dimensional space within. In other words, the black hole's interior might exist in a higher dimensional informational layer, while we perceive only its shadow in our familiar spacetime. Visualizing this dimension is like trying to see the code behind your computer screen. The images and motions appear smooth, but beneath the surface, there's a hidden architecture of bits and logic gates. Similarly, the universe's source code could operate in an informational dimension we can't directly perceive, with physical laws emerging from deeper computational rules. Some theorists even suggest that quantum entanglement, where particles instantaneously influence each other across vast distances, might be a glitch in this cosmic program, a shortcut in the data processing that bypasses the usual speed limits of spacetime. Experiments are already probing these ideas. Quantum computers manipulate information in ways that classical physics can't explain, hinting at underlying informational structures. Meanwhile, researchers studying the cosmic microwave background hunt for anomalies patterns that might reveal the universe's pixelation, like detecting the resolution of a digital display. If information truly is a fundamental dimension, then reality as we know it might just be the user interface for something far stranger, a hidden layer of code humming beneath the surface of everything. And if we ever learn to read it, we might not just understand the universe, we could rewrite it. Imagine if every particle in the universe had a secret twin, a heavier, mirrored version of itself lurking just out of sight. This isn't science fiction, it's the elegant promise of supersymmetry, a theory so compelling it's been called the missing piece of modern physics. SUSY, as it's known, proposes a cosmic symmetry where every fermion, like electrons and quarks, pairs with a boson, like photons, and vice versa. These hypothetical sparticles would solve some of physics' greatest puzzles, from unifying forces to explaining dark matter. But here's the twist: despite decades of searching, we've found exactly 0 sparticles. So where are they hiding? The answer might lie in the very fabric of spacetime, tucked into dimensions curled so tightly, even our most powerful colliders can't pry them loose. Take the Large Hadron Collider's hunt for SUSY particles. Designed to smash protons together at nearly light speed, the LHC should have produced sparticles if they existed at the energies predicted. Yet after trillions of collisions, the detectors remain silent. One explanation: these elusive partners might not be absent, just displaced, flickering between our three-dimensional world and extra dimensions like ghosts slipping through walls. Picture a sparticle not as a static object, but as a vibration threading through higher dimensional space, only briefly intersecting with our reality before vanishing again. The math supports this. In some string theory models, sparticles could gain mass by living partly in compactified dimensions, making them too heavy for current colliders to create. The implications are staggering. If sparticles dance through extra dimensions, their absence isn't failure, it's a clue. Future colliders, like the proposed Future Circular Collider with energies 7 times the LHC's, might finally reach the threshold where these hidden partners emerge. Alternatively, gravitational wave observatories could spot anomalies betraying extra-dimensional sparticle interactions. There's even a wilder possibility. Some sparticles might be entirely confined to higher dimensions, detectable only through their gravitational whispers. Critics argue SUSY flexibility, its ability to move the goalposts by adjusting sparticle masses, makes it untestable. But supporters counter that nature has no obligation to fit our timetables. After all, the Higgs boson took 50 years to find. Whether supersymmetries, hidden partners await discovery or fade into the annals of beautiful but wrong ideas, their pursuit has already reshaped physics, pushing us to consider that the universe's answers might not just be unseen, but unseeable, vibrating silently in dimensions beyond our grasp. The hunt continues not just for particles, but for the very architecture of reality itself. Imagine floating in an endless void, not as a body, not as a person, but as a lone, self-aware brain, spontaneously assembled by random quantum fluctuations. This is the nightmare scenario of the Boltzmann brain paradox, a thought experiment so unsettling it threatens to undermine everything we think we know about reality. The original idea, born from thermodynamics, suggests that in an infinite universe, it's statistically more likely for a fully formed, conscious brain to simply pop into existence out of chaos than for an entire ordered cosmos like ours to emerge. Now take that horror show and project it onto the canvas of higher dimensions where the rules of probability, entropy, and even consciousness might twist into unrecognizable shapes. In a multidimensional universe, the Boltzmann brain paradox doesn't just deepen, it fractures into infinite variations. Picture a four-dimensional space where time behaves like just another spatial dimension. Here, a Boltzmann brain wouldn't flicker into existence for a fleeting moment. It might instead unfold like an intricate origami sculpture, its consciousness stretching across timelines we can't comprehend. Or consider a brain world scenario where our three-dimensional reality is sandwiched between higher dimensional bulk. Could a Boltzmann brain form not in our universe, but in the bulk itself, a hyperdimensional observer peering into our world like a god watching ants? The real question isn't just whether these freak observers could exist, but whether they'd outnumber us. Some calculations suggest that in higher dimensions, the phase space, the range of possible states explodes exponentially, making Boltzmann brains even more probable than in our familiar three dimensions. Imagine a cosmic dice roll where every extra dimension adds 1,000 new faces to the die, tilting the odds further toward chaos over order, the chilling implication. If higher dimensions exist, we might not be the universe's intended audience at all, just a fleeting statistical blip in a sea of disembodied minds. Yet there's a counterargument buried in the math. Certain string theory models propose that compactified dimensions, those curled up at tiny scales, could actually suppress Boltzmann brain formation by limiting the ways information can arrange itself. It's like trying to build a house of cards in a hurricane. The tighter the space, the harder it is for randomness to assemble something coherent. If true, our three extended dimensions might be the perfect Goldilocks zone, roomy enough for complex structures like galaxies and life, but constrained enough to keep phantom brains from outnumbering real ones. Visualizing this is like stepping into a surrealist painting. Picture a disembodied brain suspended in a fractured kaleidoscope of dimensions, its thoughts branching into timelines that loop and knot like tangled string. Some branches dissolve into entropy while others stabilize, convinced as we are that their reality is the only one. The terrifying beauty of this paradox is that it forces us to confront the fragility of our own existence. If higher dimensions make Boltzmann brains inevitable, then every memory, every scientific discovery, even this very moment, could be nothing more than a fleeting hallucination in a hyperdimensional void. Or perhaps, just perhaps, the fact that we're here to ponder the question at all is the best evidence we have that some dimensions are sanctuaries, places where consciousness isn't a cosmic accident, but a story the universe meant to tell. What if time isn't a one-way street but a tangled knot of possibilities, where the past, present, and future loop back on themselves like a Möbius strip? Hidden dimensions might not just warp space, they could twist time itself into closed loops, allowing events to fold back onto their own beginnings. This bizarre possibility isn't science fiction. It's rooted in hard mathematics, traced back to Kurt Gödel, the same genius who shattered our understanding of logic with his incompleteness theorems.
In 1949, Gödel stunned Einstein by discovering a solution to his general relativity equations that permitted closed time-like curves, paths through spacetime that circle back to their starting point, like a snake swallowing its own tail. Gödel's universe was a rotating cosmos where the sheer spin of matter and energy twisted spacetime into helical corridors. Travel far enough along these spirals, and you'd return to your own past without ever changing direction. The key: extra dimensions. In Gödel's model, the rotation wasn't confined to the three spatial dimensions we know. It involved hidden geometries, higher dimensional vortices that bent time into pretzel-like shapes. Visualize this like a record spinning on a turntable. From above, you see a flat circle, but tilt it and you notice the third dimension, the thickness of the vinyl allowing the groove to loop continuously. Now imagine that groove is time and the thickness is a hidden dimension curling beneath our perception. The Möbius strip offers another eerie metaphor. Take a strip of paper, twist one end and tape it into a loop. Run your finger along its surface and you'll eventually return to your starting point, but flipped upside down. Now replace the paper with spacetime and the twist with an extra dimension. A particle traveling this path wouldn't just revisit its past, it might return as its own antiparticle, its quantum states inverted. Some quantum gravity models suggest these loops could explain entanglement, spooky action at a distance. What if instantaneous connections between particles are actually shortcuts through folded time? Of course, Gödel's solution required conditions we don't observe, like a universe saturated with rotating dark matter. But modern theories like string theory and brainworld cosmology revived the idea with new twists. In some higher dimensional brane scenarios, gravitational leakage into the bulk could create localized time loops, like whirlpools in a river where the current briefly flows backward. Wormholes, often imagined as spatial shortcuts, might also function as temporal bridges if their mouths move relativistically, a possibility first explored by Kip Thorne. Picture a wormhole stretched near a black hole where time slows to a crawl. One end ages minutes while the other passes millennia, effectively turning the tunnel into a time machine. The most haunting implication: if closed time-like curves exist, free will might be an illusion. Every choice you make could already be woven into the loop, predestined by the very act of your future self influencing the past. Some physicists sidestep this with the self-consistency principle. No paradoxes are allowed, so any time traveler's actions must align seamlessly with history. Others propose branching timelines or quantum multiverses where each loop spawns a new reality. Experiments remain elusive, but subtle clues might hide in cosmic rays. If time loops exist, particles could circle them endlessly, gaining energy until they punch through as ultra-high-energy anomalies. Others suggest searching for impossible quantum correlations, particles that seem to remember futures they haven't experienced yet. For now, dimensional time travel lingers at the edge of theory, a tantalizing reminder that the universe's strangest secrets might not lie in the stars, but in the invisible folds of time itself. If the universe has a grand finale, a theory so complete it ties every dimension, every force, every flicker of existence into a single, shimmering equation, it might look something like this: a cosmic symphony where the notes are dimensions themselves, vibrating in perfect harmony. This is the dream of the ultimate ensemble theory, a framework so vast it doesn't just describe hidden dimensions, it is them woven into the very fabric of reality. At its heart lies a radical idea that every mathematically possible structure isn't just a blueprint for a universe, but a universe in its own right, humming in some corner of the multiverse. Max Tegmark's level Roman IV multiverse takes this to its logical extreme, proposing that every consistent mathematical equation must correspond to a physical reality, each with its own unique dimensional architecture. Picture a hypercube, not just the tesseract of sci-fi lore,
but a multidimensional lattice where every vertex represents a universe with different dimensionality. One point might be a two-dimensional flatland, another a seven-dimensional realm where gravity knots itself into braids, yet another a fractal cosmos with infinite fractional dimensions. The hypercube itself isn't just a metaphor, it's a shadow cast by the true structure of the multiverse, a higher dimensional map of possibilities where every path, every connection is a valid configuration of existence. Tegmark's vision erases the line between math and physics entirely. In this view, pi isn't just a number, it's a universe where circles are inevitable. Prime numbers aren't abstractions, they're the vibrational frequencies of strings in a cosmic code we're only beginning to crack. The implications are dizzying. If the ensemble theory holds, our universe's three spatial dimensions aren't special, they're just one combination in an infinite library of geometries. Somewhere in the multiverse, there's a reality where gravity operates in 5 dimensions, making black holes into hyperspirals instead of singularities. Another might have time branching like a river delta, with every decision spawning divergent currents. The most haunting possibility: there could be universes where dimensions change over time, unfurling like petals or collapsing into threads, rewriting the laws of physics on the fly. Critics argue this strays into metaphysics, that without empirical tests it's more philosophy than science, but supporters point to eerie alignments. The fact that our universe's constants are finely tuned for life fits neatly into the level Roman 4 multiverse. We simply inhabit one of the rare mathematical structures where consciousness can arise. Even quantum mechanics' notorious measurement problem takes on new light. What if wave function collapse isn't a physical process, but a dimensional one, with every outcome realized in some branch of the hypercube? Visualizing this demands stretching imagination to its limits. Think of a kaleidoscope, but instead of colored glass, its mirrors reflect entire cosmoses. Give it a twist and the pattern shifts, a new set of dimensions clicks into place, a new universe crystallizes. Now imagine every twist, every possible configuration exists simultaneously in a hyperdimensional superposition. We're not just stardust, we're a single equation in an endless cosmic proof, one scribble in the margin of a notebook we'll never see the cover of. The ultimate ensemble theory doesn't just unify physics, it redefines what real means. If Tegmark is right, then every time a mathematician scribbles an untested conjecture, they might be drafting the blueprint for a universe. Every unsolved problem, from the Riemann hypothesis to the Navier-Stokes equations, could be a hidden dimension waiting to be explored, not with telescopes but with pure thought. The boundary between discovery and creation blurs. The cosmos isn't just stranger than we imagined, it's stranger than we can imagine. A fractal mosaic of mathematical realities where dimensions aren't just hidden, they're infinite, they're inevitable, and in some sense they've been waiting for us all along. From vibrating strings curled in 6-dimensional shapes to entire universes existing millimeters away in a dimension we can't perceive, the theories we've explored today stretch the limits of imagination and science itself. Hidden dimensions aren't just abstract math tricks, they could be the keys to unlocking the universe's greatest mysteries, dark matter's invisible grip. Maybe particles anchored to a shadow brain, gravity's puzzling weakness, a force leaking into higher dimensional space like water through a sieve. Even consciousness itself might ripple through dimensions we can't measure, weaving our reality into a far grander cosmic tapestry. Some ideas feel ripped from fantasy wormholes stitching space-time together, black holes birthing new universes in their depths, or the chilling possibility that we're living in a hyperdimensional simulation. Yet these aren't bedtime stories, they're serious attempts to reconcile quantum weirdness with cosmic order, propelled by equations scribbled on whiteboards and data from billion-dollar colliders. The wildest part, any one of these theories, if proven, wouldn't just tweak physics, it would rewrite reality's rulebook entirely. Imagine waking up to headlines confirming holographic duality, where everything you see, touch, and love is a cosmic mirage projected from a two-dimensional boundary. Or picture scientists announcing gravitational anomalies that betray a fifth dimension warping our universe from within. Here's the thrilling truth: we're living through a revolution in understanding. Every unanswered question, why the cosmos seems fine-tuned for life, what lurks beyond a black hole's edge, whether alternate realities hum just out of reach, might find its answer curled up in dimensions we've yet to map. The next breakthrough could come from a lab, a telescope, or even a glitch in quantum code no one expected. So tell us which dimension fascinates you. The holographic universe's pixelated edges, the cosmic symphony of string theory's hidden folds, or something wilder still? Drop your thoughts below and don't forget to subscribe. The universe has more secrets to spill, and we're just getting started.